So on Wednesday, right, we learned what the definition of a rational function is, right? It's a quotient with a polynomial in the numerator and a polynomial in the denominator. And the domain for a rational function is a set of all real numbers except for those values of x that make the denominator equal to 0. Right, so we had these two examples of rational functions. We found the domain for each of these, right, by finding the values of x that make the denominators equal to 0. And then we found the x and the y intercepts. Okay. And then we, for a particular rational function on page 2, right, we investigated asymptotic behavior for that rational function. Right? So where the denominator was equal to 0 in this case, right, is where the vertical asymptote occurs. And then we also investigated the end behavior in the graph of that rational function. Okay? So rational functions can have two kinds of asymptotes: vertical asymptotes and horizontal asymptotes. Okay? The horizontal asymptotes just have to do with the end behavior in the graph of the function, the left end and the right end behavior. You know, with a polynomial function, right, on each end the graph either goes up or it goes down. With a rational function, it can go up, go down, or flatten out to the right or to the left. Okay. All right, and then at the top of page 3 of your notes, it gives a formal mathematical definition of a vertical asymptote and a formal mathematical definition of a horizontal asymptote. There are 3 conditions that we have to consider in finding horizontal asymptotes. The equation of the horizontal asymptote, remember, horizontal asymptote is a horizontal line. And so the equation of the horizontal line for the horizontal asymptote will be y equals 0, or y equals some real number, or the graph won't have a horizontal asymptote because the graph either goes up or goes down on each end. Okay. And then I commented about a special case of a special kind of asymptote called a slant asymptote. When the degree of the numerator exceeds the degree of the denominator by 1, then the graph of the rational function will have a slant asymptote, and the equation of that slant asymptote is the equation of a straight line. And we'll learn how to find that equation today. Okay. So in the examples that follow, right, we got 1, 2, 3, 5 examples, right? We're going to graph 5 rational functions. Okay. So are there any questions or concerns before we get started? All right. So in example 3, we're going to find the so I'm not going to write on the board, okay? I'm going to do this on the using the document camera, right? Because of the graphing, because of the grid. So we're going to find vertical, horizontal slant asymptotes and check for intercepts. Also sketch the graphs of the given rational function. So we're going to do this for each case. Okay. So the first rational function is f of x is equal to 2 over x minus 1. And first thing we got to find is the domain in interval notation. So the domain in inequality notation, just writing off to the side here, is you set the denominator not equal to 0. Okay. If you can't, sometimes I forget where this is positioned on document camera, so if you can't see what I'm writing, right, please say something. And then when you solve for x, right, you get x can equal 1. So domain's all real numbers except for the number 1. So in interval notation, it's minus infinity to 1, parentheses, union, parentheses 1, to plus infinity. Okay. Now, the last thing that we're going to find is the range in interval notation, right? Well, typically we use the graph to find that. Okay. The equation of the vertical asymptotes asking for the equation or equations of the vertical and the horizontal asymptotes, okay? So for the vertical asymptotes, first you gotta make sure is that the rational functions in reduced form, right? There are no common factors in the numerator and denominator, which there aren't. So you set the denominator equal to 0, and then you solve for x. And so we get the vertical line, x equals 1, is a vertical asymptote. So over here in our grid, right, at x equals 1 on the x-axis, I'm going to draw a vertical line that goes through 1 on the x-axis. That's our vertical asymptote. The graph is either going to go up or go down on each side of that vertical asymptote. Okay. Next, we got to find the horizontal asymptote. Okay. Now, I said that there were 3 cases, okay, with horizontal asymptotes. Right? The equation of the horizontal asymptote is either going to be y equals 0, y equals some real number, or there won't be a horizontal asymptote. Okay. So here's our rational function, right, in general terms, in mathematical terms. The polynomial in the numerator is degree n. The polynomial in the denominator is degree n. So this says if n is less than m. So if the degree of the polynomial in the numerator is less than the degree of the polynomial in the denominator, we call that bottom heavy. Okay? And if it's bottom heavy, right, the rational function is bottom heavy, then the equation of the horizontal asymptote, which is a horizontal line, is y equals 0. So in our example down below here, the degree of the numerator is 0, right? There's no x, so the degree is 0. And the degree in the denominator is 1. Right? That's x to the first power. So that's degree 1. And since the degree of the numerator is less than the denominator, we call that bottom heavy. And so since this rational function is bottom heavy, the equation of the horizontal asymptote is y equals 0. The horizontal line, y equals 0. Now the horizontal line, y equals 0, coincides with the x-axis, right? The x-axis crosses the y-axis at 0. I put my y in the wrong place. So this is the y-axis, okay? And so the horizontal line, y equals 0, and the x-axis, right, coincide. So the graph of this rational function is going to flatten out above or below the x-axis on the right, and above or below the x-axis on the left, okay, for end behavior. But we have to figure that out, whether it's above or below the x-axis. The x-intercepts, okay, we talked about the x-intercepts. Well, let's do y-intercept. That's the easiest, right? The y-intercept is y equals f of 0. And when you put 0 in for x up here, right, you get 2 over 0 minus 1, which is negative 2. Okay. So the y-intercept is y equals negative 2, or the point 0 minus 2 and a quarter. Okay. So we can plot that point, right? Here's the x-axis, right? So here's the y-axis, and here's minus 2 on the y-axis. So our graph, okay, is going to go through that point, right, on the y-axis, 0 minus 2. All right, to find the x-intercepts, right, remember there are no common factors in the numerator and denominator, To find the x-intercepts, you set the numerator equal to 0 and solve for x, right? Well, 2, the numerator 2 can't equal 0, so there is no x-intercept. Okay. So we just write none. Nowhere does the graph of this rational function, okay, cross the x-axis, cross or touch the x-axis. Okay. Is everybody with me so far? All right. So now we can graph this thing. Okay. Now, what I suspect, because this is the y-intercept, the graph's going to go down to the left of x equals 1, right? The vertical line x equals 1, and then flatten out to the left under the x-axis. Right? It's going to look something like this. But let's verify that it goes down here. Okay. So to determine whether the graph goes up or down on the left side of the vertical asymptote, we just have to use a value of x less than 1, slightly less than 1, and determine if the value of the function is positive or negative. If it's positive, that means the graph goes up. If it's negative, it means the graph goes down. So 0.9 is just less than 1. So if I evaluate the function at 0.9, I get 2 over 0.9 minus 1, which is equal to negative 20. So since that's a negative number, that tells me the graph goes down to the left of the vertical asymptote. Okay. And since the x-axis, or the horizontal line y equals 0, is a horizontal asymptote, conclude it flattens out going to the left like that, right? As you go up further to the left, it gets closer to the x-axis, graph gets closer to the x-axis, but it doesn't cross or touch it. Okay. Now we got to do the graph to the right of x equals 1. Okay. So does the graph go up or go down to the right of x equals 1? Well, I use a number just slightly larger than 1 on the x-axis, so I use 1.1. And when I evaluate the function at 1.1, I have 2 over 1.1, which is equal to, oh, excuse me, that's 1.1 minus, sorry, 2 over 1.1 minus 1, which is equal to plus 20. So that tells me that the graph goes up, right, to the right of the vertical asymptote. And since the x-axis, the horizontal y equals 0 is a horizontal asymptote, I conclude it flattens out going to the right like that. And now we have the graph of the rational function. Okay. Now the last thing we got to do is find the range in interval notation. Remember, the range are the y coordinates, right? So the graph goes down forever here, so there's no minimum y coordinate. And then as we go up the graph, this part of the graph gets closer and closer to y equals 0 as we go out to the left, but the graph never touches the x-axis, so there's no y coordinate of 0. And so that part of the graph, the y coordinates are all less than 0. So there's not a bracket there, there's a parenthesis, because the graph never touches the x-axis. And then to the right of the vertical asymptote, the graph gets closer and closer to the x-axis, the line y equals 0, but never touches it. And so the y coordinates are all greater than 0, okay, to the right of the vertical asymptote. And then the graph goes up forever, so there's no maximum coordinate. And so the range and interval notation is all real numbers except for the number 0. Now, alternatively, instead of using the graph to figure out the range, right, you can see this is a one-to-one function, right, passes the horizontal line test. And so you could find the inverse function for f of x and use the domain of the inverse function to find the range of f of x, okay? But that would require more math. So you can either use the graph or use the inverse function to find the range of f of x. Okay. Any questions on that, ladies and gentlemen? All right, if you flip over your document, your handout, we'll take a look at B. So f of x is equal, so now that we've been through this, right, we can start speeding things up, hopefully a little bit. Okay. So f of x is equal to 3x plus 2 over 2x plus 4, okay? No common factors involving x in the numerator and denominator. Domain and interval notation, set the denominator 2x plus 4 can equal 0. So that's our domain, right? All real numbers except for the number minus 2. The equation of the vertical asymptote, right? Again, there are no common factors in the numerator and denominator. So we set the denominator equal to 0, and you get x is equal to minus 2. You'll notice that in the example before and the example here, right, the vertical asymptotes occur for those values that are not in the domain of the function. Okay? There's only one caveat, and that's where there's a hole in the function that you have to be careful of. All right. The horizontal asymptote, the degree of the numerator is 1. The degree of the denominator is also 1. Excuse me. Right? So they're equal degree. Right? So this is not bottom heavy like in the previous example. Okay. So if you flip over to the previous page, this scenario falls under case number 2, where the degree of the numerator and the degree of the denominator are equal. And when they're equal, the equation of the horizontal asymptote is y equals a real number, and that real number is equal to the leading coefficient of the numerator divided by the leading coefficient of the denominator. Okay. So, in this example, I want to emphasize, we're writing equations. Okay? An equation, vertical and the horizontal asymptotes are lines, vertical lines and horizontal. So in this example, the leading coefficient of the numerator, right, is 3, and the leading coefficient of the denominator is 2. Remember, the leading coefficient goes with the leading term, and the leading term is the term with the largest power of x. Okay. All right. So we have a vertical asymptote. X equals minus 2 is a vertical asymptote. So we draw a vertical line that crosses the x-axis at minus 2. And then y equals 3/2, okay, is a horizontal asymptote. And so, 3/2 is 1.5. So now we've drawn our vertical and horizontal asymptote, okay? And that should help graph with our graphing. All right, x-intercepts. Right, or let's do, I always like doing y-intercept first. So the y-intercept, right, is y equals f of 0. And so when you put 0 in for x, right, you have 3 times 0 plus 2 over 2 times 0 plus 4. And that equals 2/4 or 1/2. So our horizontal asymptote, or y-intercept, excuse me, is y equals 1/2, or the point 0, 1/2. So here's 1/2 on the y-intercept right here. So that's where the y-intercept. So I suspect in the graph of this rational function, right, it goes down to the left, to the right side of the vertical asymptote, and then flattens out to the right. But we don't know for sure. Okay. Now for the x-intercept, right, no common factors, numerator and denominator. You set the numerator equal to 0. Solve for x. And you get x is equal to minus 2/3. So the x-intercept, x equals minus 2/3, or the point minus 2/3, 0. So minus 2/3, right? Is that roughly right? So now I'm really sure that, pretty sure that the graph, right, goes down to the left, to the right of the vertical asymptote, and then flattens out to the right. All right, but here it says something new. It says check for crossing HA. HA is short for horizontal asymptote. It is possible that to the far right end, right, the graph will flatten out either above or below the horizontal line y equals 3/2. But in the middle here, in the middle of the graph, it might cross the horizontal asymptote and then flatten out above it. Okay, instead of flattening out below it to the right. Okay, and you can have the same thing on the left. So we got to check to see if that happens, right? Does the graph cross the horizontal asymptote? Okay. So the equation of the horizontal asymptote is y equals 3/2. Okay, excuse me. The equation of the horizontal asymptote is y equals 3/2. And you know, y values and function values are the same. So we replace f of x up here with 3/2, and we solve for x. And if we're able to solve for x, that means there's an x coordinate, right, where the graph is on the horizontal asymptote. Okay. So the right half, f of x is equal to 3x plus 2 over 2x plus 4. And we set that equal to 3/2, right? Because our horizontal asymptote is y equals 3/2. It crosses the y-axis at 3/2. And now we solve this equation for x. And if we get x equals a real number, then there's a point on the horizontal asymptote where the graph crosses or touches the horizontal asymptote. Okay. So got fraction on the left equals fraction on the right. So we can do cross multiply. And so we have 2 times 3x plus 2 is equal to 3 times 2x plus 4. And now when you distribute the 2 inside the parentheses, right, we have 6x plus 4 is equal to 6x plus 12. And now when you subtract 6x from both sides, end up with 4 is equal to 12, right? And you subtract 6x minus 6x is 0. 6x minus 6x is 0. And you're left with 4 equals 12, and that's a false statement. Right? 4 can't equal 12. So the graph of our function does not cross the horizontal asymptote y equals 3 halves. Okay. So since the graph goes through these 2 points, it's got a flat, right? The graph going to the right does not touch the horizontal asymptote, so it's got to flatten out like that, right? Now, and since it doesn't cross or touch the horizontal asymptote, it's got to go down and to the left here. Now, what about to the left of the vertical asymptote? Okay, does it go up or down? Okay, well, minus 2.1 is just to the left of minus 2 on the x-axis. So if we evaluate the function at f of minus 2.1, you do that math, the numerator equals minus 4.3, denominator equals minus 0.2, and negative over negative is positive. So the graph goes up on the left side of the vertical asymptote. And then it's got to flatten out above the vertical asymptote or above the horizontal asymptote to the left, because it doesn't touch it. Right? We verified down here that the graph, that the graph does not cross or touch the horizontal asymptote in the middle. Okay. So you can see now, so any questions on getting the graph? So you can see now the y coordinates for the range. There's no minimum y coordinate, right? Because it goes down forever here. And then it flattens out to the right here, and it gets closer and closer to y equals 3 halves, but it never reaches y equals 3 halves. So for this part of the graph, all the y coordinates are less than 3 halves. And on the left here, right, as it goes out, the graph goes out to the left here, it gets closer to y equals 3 halves, but doesn't touch it, doesn't reach it. And so all the y coordinates for this part of the graph are greater than 3 halves. Right? There's no maximum y coordinate, right? So they go to infinity. And again, this is a one-to-one function, so if you wanted to, you could find the inverse function for f of x, and then use the domain of the inverse function to find the range of f of x. Okay. But if you can read the graph, it's obviously a lot faster. Okay. Any questions on that, ladies and gentlemen? Okay. All right, in C, you notice that as we go from A to B to C to D to E, right, we're ratcheting things up a little bit. So in C, we have to factor the numerator. And 2x squared minus 2, you can factor out 2 and you have x squared minus 1. And x squared minus 1 factors into x minus 1 times x plus 1. You should be able to verify my factoring. It's simple enough. Okay. And then the denominator is already factored, right? It's x plus 2 times x minus 3. Okay. So there are no common factors in the denominator. Okay. So I'm finding the domain. we set the denominator equal to 0, right? And that's already factored, so by the zero product property, either x plus 2 can't equal 0, and x minus 3 can't equal 0. Okay. And so when you solve both those for x, right, you get x can't equal negative 2, and x can't equal 3. So in interval notation, the domain is minus infinity to minus 2, union minus 2 to 3, union 3 to infinity. Now to get the vertical asymptotes, right? The vertical asymptotes occur, right? You set the denominator now equal to 0, and you get x is equal to minus 2, and x is equal to 3. So this graph has two vertical asymptotes. So here's the vertical asymptote, right? The vertical line, x equals minus 2. And here's the vertical asymptote, the vertical line, x equals 3. Now, the equation of the horizontal asymptotes. Okay, now this one makes things a little trickier. Okay, because the numerator is unfactored, the denominator is factored, and so we need to know the degree of the numerator and the degree of the denominator. Well, we already know that the degree of the numerator is 2. Okay. So let's do this. If I FOIL the denominator, I have x squared, right? The denominator FOILs into x squared minus x minus 6, right? And now you can see that the degree of the numerator is 2, and the degree of the denominator is 2. Okay. They're equal degree, and so the equation of the horizontal asymptote is y equal, right, the leading coefficient of the numerator over the leading coefficient of the denominator. Leading coefficient of the numerator is 2. Leading coefficient of the denominator is 1. So it's 2 over 1, or 2. So y equals 2, the horizontal line y equals 2 is the horizontal asymptote. So we got 2 vertical asymptotes and 1 horizontal asymptote in the graph of this rational function. Okay. All right. To find the x-intercepts, okay, you set the numerator equal to 0, right? So we have 2 times x minus 1 times x plus 1 is equal to 0, right? And you know, by the zero product property, right, either x minus 1 is equal to 0 or x plus 1 is equal to 0, which means x equals 1 or x equals minus 1. X equals 1, x equals minus 1 are the x-intercepts. Okay. So we have up here x equals minus 1, or the point minus 1, 0, and x equals 1, or the point 1, 0 are the x-intercepts. Okay. So here's minus 1 on the x-axis, here's plus 1. Okay. So unless this graph, I can't imagine how in the middle of the graph could cross the horizontal asymptote. I suspect it's going to go down to the left here and down to the right here. Okay. Define the y-intercept. You evaluate the function at f of 0. Okay. And that might be easier to use this, right? You can use this up here, or this up here, or this right here. And you notice that when you put in 0 in for x and find the y-intercept, right, all you're ended up is a constant term in the numerator and constant term in the denominator. And you get minus 2 over minus 6, which is 1/3. So y equals 1/3, or the 0.013 is the y-intercept. Okay. And so 1/3 is roughly right here. So now I'm really pretty confident that the graph goes down to the left here, down to the right there. Okay. Now to see if it crosses, you got to check for the graph crossing the horizontal asymptote. Okay. Again, the equation of the horizontal asymptote is 2, right? Y equals 2. So we set, now you can do any of these three versions of f of x. I use this one. Okay. Set the right-hand side of f of x equal to 2 and solve for x. So you can get a value of x. Okay. So we have 2x squared minus 2 over x squared minus x minus 6 is equal to 2. Okay. And now in solving for x, right, we got to multiply both sides by the denominator, x squared minus x minus 6, declare the fraction on the left. Okay. And so we have 2x squared minus 2 is equal to 2 times x squared minus x minus 6. And then when you distribute the 2 inside the parentheses, we have 2x squared minus 2x minus 6. Okay. And when you subtract 2x squared from both sides, right, they cancel. Right, they go away. 2x squared goes away when you subtract 2x squared from both sides. And then if we add 2x, right, move the 2 minus 2x to the left-hand side by addition, and the minus 2x to the right by addition, we have 2x is equal to negative 4. And we divide both sides by 2, you get x is equal to negative 2. So the graph, yes, sir.
And the step up there, you did 2 times negative 6, you put negative 6. Negative 4.
Oh, thank you very much. Okay. Yeah, should be negative 12. Sorry. Yep. So that's going to affect the value. So again, we add 2x to both sides, and we add 2, and we get negative 10. And divide by 2, we get x equals negative 5. So here's negative 5 on the x-axis. So the graph crosses or touches, okay, the horizontal asymptote at minus 5. It actually crosses. So define the y-coordinate, right? Yeah. So you could put in minus 5 in for x, evaluate the function x equals minus 5, and you would get, right, or you can just by visual inspection, if it crosses the horizontal asymptote at y equals minus 5, the y coordinate is 2. So minus 5, 2 on the graph. All right. So we're getting a little pinched on time, but if you evaluate this function at minus 1.9, okay, you'll see that it's negative, the value of the function is negative, so the graph goes down here. And if you evaluate the function at 2.9, you'll see that the value of the function is negative. And so the graph goes down like this. Okay. Now if I evaluate the function at 3.1, which is just slightly greater than 3, I get a positive value for the function. So that tells me it goes up to the right of that vertical asymptote, and then it's got flattened out going to the right. And similarly, okay, if I evaluate the function just to the left of minus 2 on the x-axis, at minus 2.1, I get the value of the function is positive again, which means it goes up to the left of the vertical asymptote. But we know it crosses the horizontal asymptote at minus 5. So I'm going to extend my horizontal asymptote. And crosses the horizontal asymptote, and then it flattens out to the left. Right below the horizontal asymptote like that. So you can have that, you can have a horizontal asymptote where part of the graph crosses the horizontal asymptote. So let me get a tangent. So, as I said, we covered crossing of the horizontal asymptote. So you can do like 99% of the homework, 9 out of 10 problems, if you so desire. Sorry. Laura? Sam? Dallas?
Here.
Anders? Kirsten? Grace?
Here.
Nevia? Jake?
Here.
Mia?
Here.
Joe?
Here.
Brianna?
Here.
Enzo? Annabelle?
Here.
Alex?
Here.
Nicole? Kayla?
Here.
Aiden?
Here.
Claudia?
Here.
Angelica? Melissa? Hannah?
Here.
Haley? Jeffrey?
Here.
Oliver?
Here.
Amaya?
Here.
Have a good weekend. I'll see you Monday.
Oh, yeah.